This video shows how to evaluate the famous Dirichlet integral using Feynman's parameter technique. This method appears frequently in advanced calculus courses and mathematical physics applications. You'll learn to introduce a parameter, differentiate under the integral sign, and solve the resulting differential equation. We'll use Feynman's trick, differentiation under the integral sign. We introduce an exponential damping factor e to the negative tx, which lets us kill the troublesome x in the denominator when we differentiate. We find I prime of t equals negative 1 over t squared plus 1. Integrate back and set t to 0. Let's work through it on the diagram. The integral of sine x over x from 0 to infinity. It's called the Dirichlet integral, and it equals pi over 2. But how do you prove it? Standard techniques fail here. There's no elementary antiderivative for sine x over x, integration by parts loops, and substitution goes nowhere. Goal: evaluate the Dirichlet integral using Feynman's differentiation trick. Step 1. We introduce a parameter t by multiplying the integrand by e to the negative tx. This defines a new function I of t. I of t equals the integral from 0 to infinity of e to the negative tx times sine x over x. When t equals 0, the exponential disappears and we recover the original integral. When t goes to infinity, the exponential kills the integrand, so I of infinity is 0. This gives us our boundary condition. Now comes the key move. Differentiate I of t with respect to t. Step 2. We apply Leibniz's rule, differentiate under the integral sign with respect to t. I prime of t equals the integral of the partial derivative with respect to t of the integrand. The derivative of e to the negative tx with respect to t brings down a factor of negative x. The x in the numerator cancels with the x in the denominator. This is the whole point of Feynman's trick. This is a standard Laplace transform. The integral of e to the negative tx sine x equals 1 over t squared plus 1. Beautiful. Now we just integrate I prime of t to recover I of t. Step 3. We integrate I prime of t to find I of t, then use the boundary condition. Integrating negative 1 over t squared plus 1 gives negative arctan of t plus a constant c. Using our boundary condition, I of infinity equals 0. Since arctan of infinity is pi over 2, we get c equals pi over 2. So I of t equals pi over 2 minus arctan of t. Finally, setting t to 0. Arctan of 0 is 0, so I of 0 equals pi over 2. Whenever you see an integral where dividing by x blocks standard methods, consider Feynman's trick. Introduce an exponential parameter that cancels the x upon differentiation. Multiply by e to the negative tx, differentiate under the integral to kill the denominator, then integrate the resulting elementary form and apply boundary conditions. The Dirichlet integral equals pi over 2. A beautiful result, made accessible by one of the most elegant tricks in analysis.